What is speckle? Speckle are the result of the superposition of many random wavelets. So if you look at the image, it's grainy, it's not smooth. We can see the tissue, but we can also see some graininess in the image. High intensity, sometimes it's low intensity. So this occurs because random wavelets are superposition with one another, and this is generated. Now we'll do this tutorial in two ways. One is that how can we detect the speckle? What is the quantitative measurement of the speckle? Then in the next part we'll talk about how can we remove the speckle from the image. So one way to track the speckle is you can do the correlation analysis. The way we can do the correlation analysis to track that how the speckle pattern is changing over time. Say for example, we have a reference image here. Say we have a reference image here, and over time, like how, say for this position of the image, how it's changing over time. So this is at t equal to 1 second, and this is say t equal to say 10 seconds. Same position, same tweezer, we'll try to see how it's changing. So one way to do is that we can calculate the correlation. So first, so this is a reference image. The first image is a reference image, and for this area we are calculating the cost correlation using this equation. So you are selecting certain portion of the image, say this portion here, and you are calculating the autocorrelation portion of the image. Reference image, and if you do the complex conjugate of the reference image of that portion, and finally if you do the IFFT, then you will find the autocorrelation. So now say we are at t equal to 10 seconds here. We will do again the calculation of autocorrelation of the second part here for the image 2, same way. Now finally what we have to do is we have to calculate the cross correlation of this portion with that portion. This is the cross correlation. Now to quantify that how much they are matched or how much they did not match, this is the way. So cross correlation amount, what is the cross correlation part, and square of the autocorrelation of both of the images. And we will track this value over time, and we will try to see how things are going on. Say for example, this is our image and we have taken 3 ROI. Say this is ROI1, this is ROI1, this is ROI2, and this is ROI3. From the image we have selected 3 different ROI. And if we track from our reference image over time, this is the frame number, and each frame is about 120 milliseconds. We have taken the image of 100 frames, and the blue line is the cross correlation part, this part over time. And if you look at that, this value is changing. This is only for 12 seconds, so it's not that much changing, but its value is changing. So this is for ROI1, and the second one is for ROI2, the third one is for ROI3. So it's changing over time. And here the red line is the faded line. We have seen the similar thing for different ROI. One thing to mention is that all these data up to this figure and this figure, we have acquired the data at the imaging speed of 10 kHz. Our another goal is to see how the speckle pattern will change if we change the speed of the OCT acquisition. So this is just another data just to show, and we see this kind of changes. Now what if we change the speed? If we change the speed from 10 kilohertz to 30 kilohertz and do the same thing up on the agar data, so we can see that here in the ROI2 lot of randomness, and this line is actually all fitted. So as we have taken the data only for 12 seconds, so we don't see much difference between the 30 and 10 kilohertz speed. But if we compare of say ROI3 is 0.003 for 30 kilohertz. On the other hand, for 10 kilohertz we found 0.002. The slope value, standard deviation of the data is 0.002, and here standard deviation of data is 0.003, so it is lower. On the ROI1 we see at 30K it's 0.001. If we go to similar data set of here, so 0.002. So it means that there is a difference. That means standard deviation value is reducing when we are taking data with 30 kilohertz. What about quantitative measurement? Let's see like how does they fit quantitatively. So let's see side by side. This is with 30 kilohertz of data. Here we'll put that this is 30 kilohertz here, and I will copy another data with 10 kilohertz of speed. So this is 10 kilohertz speed data of the same sample. We have taken the agar sample, and if we look at side by side, what do you see? We see totally different. So here a lot of grainies, but here the in this image we see lot less. Here they are prominent in 30 kilohertz. What else we see? This part is not that much clear. Also, so these are the comparison image. This is 10 kilohertz speed. This is 30 kilohertz speed. So in this way actually we can track that how actually the OCD image is changing. So this is the autocorrelation part, this is the autocorrelation part, and this is the cross correlation part. This is the autocorrelation of the image 2, and this is the cross correlation between image 2 and reference image, and this is the amount just to see how it's changing. So basically we can detect, we can take the measurement how the speckle is changing over time, and later on I'll talk about how can you remove the speckle. Thank you very much.